So let's do another example of one of the basic inference rules. So for this particular example, my argument is P or Q, not P, therefore Q. And I want to figure out, is that a valid argument or not? Well, I haven't memorized table 1, and so I can't remember if this is something on table 1 in rows in section 1.6.3. So what I want to do is to be able to quickly verify whether or not this thing is a valid argument. And as we saw in the previous video, what this means is that we need to show that P or Q, one of our hypotheses, and not P implies Q. We need to show that this thing is a tautology or not. So in the last example, we used a truth table to be able to do this. And we could construct a truth table for this, but it might be a little bit tedious. And remember, we had multiple different ways to show that something is a tautology or not. For example, we could use our different rules of logic. So I'm going to show that this thing here is a tautology or not by using my rules of logic. So in this particular example right here, I know the definition of this implication. So I know that this is logically equivalent to the following. I negate my hypothesis, and then I put my conclusion right here. And so I'm going to simplify this expression, and I see a not over here, so that makes me think of De Morgan's law. So we can apply De Morgan's law. I'm going to distribute the not in here, and then I'm going to apply De Morgan's law again immediately to this inner expression. So this is going to become not P, and I flip this, not Q. When I applied De Morgan's law here, I flip that guy, and then I'm going to end up with a not P right here, which I know is a P, or Q right here. Good. So I have this expression right here, and I see that's a mixture of ands and ors right here. And I remember one of my rules that tells me how I can distribute this or P into this expression right here. So in particular, this will become, so I'm going to distribute this P into here. It's going to become a not P or P, and P or not Q. And at the very end over here, I have an or Q. Oh, here I see a not P or P. I remember that that's always true. So this thing is always true and this thing. So that means it's logically equivalent to simply P or not Q or Q, because I know that this expression right here is always going to be true. Now I just have an expression that involves ors right here. And so I remember that when I have only ors, my parentheses here don't really matter. P or not Q or Q. Well, here again, I have that same not Q or Q, and I remember from my various rules that this thing is always true. Not Q or Q, that's going to be a true statement. So I've been able to show that this is logically equivalent to P or true. Well, P or true, that's always going to be true. So yes, I have been able to successfully show that this expression right here is a tautology. This time not by using a truth table, but by using my different logical operators, De Morgan's law, associativity, distribution, etc., by simplifying this expression right here and showing that it's logically equivalent to true. So since I've had a whole lot of practice of simplifying these expressions and everything like that, I can then take this right here and verify if it's a valid argument or not. This is a tautology. It's always true. So therefore, yes, this is a valid argument. And in fact, it comes with a fancy name, and this fancy name is disjunctive syllogism. And so even if I've forgotten whether or not this particular argument right here exists on table 1 or not, since I can quickly apply my different rules of how logical operators interact with each other, I can quickly verify whether or not this is a valid argument or not without having to memorize it, because I understand the definition of what it means to be a valid argument, and I have had lots of practice to be able to apply my different rules of logical operators.